Hi guys, welcome to my YouTube channel. So today I'm going to explain what principal component analysis is, what it's used for, and I'm going to derive the theory behind PCA, which is principal component analysis. So in essence, principal component analysis is essentially a dimensionality reduction technique. All right, dimensionality reduction technique. So what that means is that, let's say I have a data set of two dimensions, which basically means that it has two columns. Let's call it column A and column B. And I have data points over here, right? Now, what if I want to project these data points onto a vector and keep that projection as my new dimension or my new column and do away with these two dimensions over here, right? So that's what PCA is used for. It's used to project the data points onto a new dimension. And that new dimension is decided by a vector. Let's call that vector U. So PCA is all about finding the most optimized vector U, all right? Because you can have thousands of vectors all around this point. You can have U this way as well. So how do you decide what vector to choose? So you basically want a vector where the variance is maximized, all right? Where the variance of the projection of the points on the vector is maximized. Because that's how the maximum amount of information will be preserved, right? So let's take this vector for example. And if I project all of my points over here, you can see that they're all cluttered around this space, right? Let me just change the color. You can easily see that if I project all these points on this vector U, they're all cluttered around the space. So not a lot of variance is preserved. And if the points are very close by, it'll be hard to differentiate one point from another. So if I take another vector U this way and I try to project the points onto this vector, it's easy to see that the points will be much further spread out, which means that the information will be preserved better, right? So that's what we want to accomplish with PCA. We want to find the vector where the variance of the projected points is maximized. So how do we go about deriving this and how do we prove it? So basically, we can pose our optimization problem this way, that we want to maximize. Sorry, just let me change the color. We want to maximize the variance of the projection of the data points on the vector U, all right? So if I have data points, let's call all these data points, let's say that they are data points x1, x2, all the way to xn, all right? And their projection on the vector U will be U transpose x. That's from linear algebra. So this becomes my optimization problem. Now, what I can do is I can change this. I can sort of manipulate this, and I can write it this way. I can write max of. So the variance of U transpose x is nothing but 1 by n summation n equals 1 to n U transpose x n minus x bar the whole square, right? So x bar is basically the mean of all of these data points, okay? And well, this is a formula for variance from your stat 101. So basically I've just changed this equation to this. I've manipulated it so that I can solve it for the optimization. So again, I'm going to sort of change this and I'm going to write this like this: 1 by n sigma n equals 1 to n. I'm going to write this as U transpose xn minus x bar into xn minus x bar transpose into u. Now, quick question, why am I allowed to do this? It's because this value here is basically just a single value, all right? And as long as I can multiply all these matrices with one another, such that I get back the single value, I can open it and expand it in this form, right? So again, now what I'm going to do is I'm going to sort of move things around a little bit in here, and I'm going to write this like this. I'll write it here. So I'm going to write it as maximize U transpose sigma n equals 1 to n xn minus x bar into xn minus x bar transpose by whole upon n. I just brought the n from outside, inside over here, into u. All right. So if you observe carefully, this equation right here is basically the formula for our covariance matrix. I'm going to call that an S, okay? So my optimization problem basically changes from maximize variance of U transpose X to maximize U transpose S U, all right? Where S is the covariance matrix, this one right here. Okay, so now how do we go about solving this is we're going to use something called Lagrange multipliers, all right? Lagrange multipliers are basically used to find the maximum or minimum of a function given a constraint. So I'm going to quickly explain what Lagrange multipliers are. If you know what they are, you can just skip the next 4-5 minutes. In case you don't know what they are, I'll explain it next in the video. So yeah, let's go about doing that. Alright, so Lagrange multipliers it's basically an optimizer, alright, which helps find a maximum or minimum of a function subjected to a constraint. Okay, so let's look at it with an example. Suppose I have a function f of x comma y, which is given by xy plus 1. Now if I plot this on a graph, the function will look something like this, all right? Now, where this is the y-axis and this is the x-axis. So now I want to find the maximum or minimum of this function subjected to a constraint. Let me write the constraint here. The constraint is that the points on this function f of xy should fall on another function g of xy, where g of xy is given by x squared plus y squared minus 1. Now, if you observe carefully, this is basically the equation of a circle, all right? Let me draw the circle here. So this is how it would look, right? So that's what I want to do. I want to find the maximum or the minimum point on f of xy, given that it lies on the function g of xy. So g of xy is our constraint over here, right? And well, so how do we go about doing that? We use a little bit of geometry over here. You can see that the point where both the circle and the function f of xy meet each other will share a common tangent, right? Like this. Yeah, so this is the common tangent. So we can say that the tangent line is shared by both the curves, and if that happens, then the normal is also connected, right? There'll be a normal to this curve at the same point where the tangent is shared. There's going to be another normal to the curve, which is going to be 90 degrees to it. So this is one normal, and this is another normal, right? And we also know through geometry that the gradient vector is also normal to the level curve. So the gradient vector is normal to the level curve, and the gradient vector is basically on this normal as well. All right. So what happens here is that we can say that the gradient of g of xy is a scalar multiple of f of xy, or the other way around. All right, since they both share a common point on the tangent and they both have normals to each other, they have gradient vectors as well. So if let me call this the gradient vector of g, all right, and let me call this the gradient vector of f, right? So it's easy to see that the gradient vectors are scalar multiples of one another. They can be a scalar multiple of 2 or 3 or 1.5 or -2, I don't know, but it's easy to see through geometry that the gradients are scalar multiples of one another. So how do we go about solving this? So that now that I know that the gradients are scalar multiple of one another, I can essentially write this equation as delta f equals lambda delta g, right? So here g is our constraint, and f is the function that we want to find the maximum or minimum of. And so how do you find the gradient? The gradient is nothing but the partial derivative of the functions. So the gradient dou f by dou x, or dou f by dou y, dou f by dou x and dou f by dou y will be given as y and x, right? Because if you take f of xy and you partially differentiate with respect to x, you get y, and then when you partially differentiate with respect to y, you get x. Similarly, the gradient of g, or the function g, it's 2x and 2y. Similarly, it's the same thing that I've done. I've partially differentiated. I took the partial derivative of g of xy, and when you take that with respect to x, you get 2x, and when you take that with respect to y, you get 2y. So from this equation right here, I can write dou f by dou x equal to lambda dou g by dou x, right? So that's y equal to lambda 2x, and then x equals lambda 2y. All right, so when you solve these equations, you will get the value of lambda to be plus or minus 1 by 2. Okay, so that's basically your Lagrange multipliers. You find the maximum or minimum of a function subject to a constraint. All right, that's all that Lagrange multipliers do, and that's what we are going to use to find the maximum of the optimization problem in our PCA. So coming back to our optimization problem in PCA, we have to maximize this U transpose SU. Right now, one way to maximize this would be to just give U an arbitrarily big value, or I can make U something like extremely large. And if the value of U, the magnitude of U, can keep changing, then well, I can just give it some value close to infinity, and I can maximize this. But that's not what I want. I just want to use U as a direction to find out in what direction to project the points x, right? I don't want to vary the magnitude of U. So I'm going to put the constraint over here that U transpose U is equal to 1. All right, this basically means that the magnitude of U does not change. It's equal to 1. You can write that as 1, 100, 1000, but as long as the magnitude U transpose U does not change, you're good to go. All right, so I'll just take it as 1 for all practical purposes. And now I want to maximize this equation subject to the constraint that U transpose U equals 1. All right, this is exactly what we learned in the Lagrange multipliers. Okay, that's exactly what we are going to do. We are going to take the Lagrangian L, and we are going to find the maximum or minimum of this Lagrangian subject to the constraint of how the unit vector changes. Okay, so this would be u and lambda. So the Lagrangian is basically u transpose su minus lambda u transpose u minus 1. All right, this is the Lagrangian. So now we need to find the partial derivative of this with respect to u. All right, because that is our constraint. We need to see how it would change if we vary u a little. Right? Now this equation is basically a quadratic. Okay, so when you find the derivative of this, you're going to basically use the same method that you use to find the derivative of any quadratic equation. So when I find the derivative of it, this would give me 2su. All right. Similarly, when I find the derivative of this, I'm going to get 2 lambda u. Okay. This is the same thing that we just learned in our Lagrange multipliers. Yeah, there's no difference here. That's the same thing that we have done. We have basically found the partial derivative of it with respect to a constraint. And now I'm going to equate this to 0. So basically what I'll get is su equals lambda u when I equate it to 0. Now this would seem very familiar to you if you know your linear algebra very well. This is the equation that describes the relationship between eigenvalues and eigenvectors. So what it's basically telling me is that if... Not yet, sorry. Yeah, so if I have su equals lambda u. So what I'm going to do is I'm going to replace u transpose su with u transpose lambda u, all right? Because, well, I just took su and I put lambda u over here, and that's my maximum, right? Maximize u transpose su. I have to maximize this. I just replaced it with lambda u. Now lambda here is a scalar, right? It's a scalar, it's not a vector. So I can just take it out. So I can write this as lambda into u transpose u, okay? And we know that u transpose u is equal to 1 because the magnitude, we don't want u to vary, right? That's a constraint. So this just becomes lambda. So this is the intuitive part over here. This basically tells that, you know, if you want to maximize, so our optimization problem basically becomes, if we want to maximize u transpose su, that's essentially equal to lambda. What this is saying is that the maximum of this is essentially equal to the maximum eigenvalue lambda. All right, so how do you find the eigenvalues? Well, you use something called SVD. When you do that, you get a matrix with lambda 1, lambda 2, all the way to lambda n, where you have n dimensions, and the lambda that corresponds to the first lambda will be the maximum lambda, okay? And the lambda and the vector that it corresponds to, the eigenvector u1, will be the maximum, will be the eigenvector that maximizes this equation, okay? So that's what we want to do. We have lambda, lambda 2, lambda n over here. We use SVD. We find all the eigenvalues, and we take the first eigenvalue, because by default you'll get them in a decreasing order. Lambda 1 will be greater than lambda 2, will be greater than lambda 3, and so on. So the eigenvector that corresponds to the first eigenvalue will be the one that maximizes this equation, and that will be the one that we use for u1. Alright, so I'll make another video on SVD and how SVD works and how you can decompose this. But for now, I just want to stop here because my goal was to derive the relationship in PC and how you actually go about finding the best principal component. So this u1, the one that maximizes, is called the principal component. Okay. Yeah. So that's it for the derivation. I'll stop here and I'll make a video on SVD very soon. I hope you liked it. If you did, just like and subscribe. Thanks.